So this will be a very short lecture on matrices. So far we have been talking about abstract linear transformations. So let's briefly turn our attention to an equivalent object, namely a matrix. So the setup is, let's start with T linear transformation between Rn and Rm. So let's I'll choose a basis here in Rn. Let x1 xn and the basis of the target space y1 ymb basis of Rn and Rm respectively. Now I could have started with just the standard basis of Rn and the standard basis of Rm, but this construction will work for any choice of basis. So the idea is that all the information about T is encoded in a set of n times m real numbers. And how do we get this? Well, let's look at T x1. I know that this, it's an element of Rm, therefore I can write it in terms of this, the target basis. And I'll write it as A I1 yi I equal to 1 to m, and ai1 are some real numbers. And so on. So I can write T xn as a linear combination of the yi's, and those coefficients I'll call ain. yi I equals 1 to m. Now, as we have seen before, for a linear transformation, if I know what it does to a basis, then I know what it does to every other vector. So all the information about this T is encoded by its action on x1, x2, xn, and as these equations show, its action on Tx1 is given completely by this m numbers ai1, where I varies from 1 to m, and so on. So let us define this array. Let A be this. Now the term array has no precise mathematical meaning. It's just a convenient way of writing. I might have as well written, if one wants a mathematically precise thing, I might as well write a n times m tuple of these. Just put all these numbers side by side. But it's more convenient to write it in this form. So this would be A1, A1n, and here I have AM1, AMN. Yeah, before I go to the next page, notice that Tx1, the coordinates of Tx1 is an element of Rm. The coordinates of Tx1 in this basis, y1 up to ym, is given precisely by the first column of this matrix. So the rows of this matrix have no meaning, no direct meaning in terms of this linear transformation T, but the columns have a very simple interpretation. Well, we know now if I want to see what T does to an arbitrary vector, let x belong to Rn, then I can write x as summation Cj xj j equals 1 to n. And then then Tx would be summation j equals 1 to n Cj by linearity Txj, and Txj itself is a sum Cj and then summation over I equals 1 to 1 to m. So this would be yeah, that's okay. Aij, and then it would be yi. And I can write this as a double sum. So I equals 1 to m, j equals 1 to n. I interchange the orders, and this would be aij, cj, and then yi. So in short, this the coordinates of this vector x are given by these sums here inside. So therefore, if x has coordinates C1, Cn, then Tx has coordinates of course, whenever we talk about coordinates, we must keep in mind that bases are involved. So coordinates always is always with reference to a specific basis. So right. So here this is summation a 1j cj j equals 1 to n, etc. A, and then the last term would be a m j cj j equals 1 to n. i.e. the coordinates of Tx are given by the matrix product A, and then you write the coordinates of x as a column vector. So this is a m cross n matrix. This is an n cross 1 matrix. So I'll get a m cross 1. column vector, and whose entries are these things here. So all this is, I assume that you have seen all of this. It just, the reason I'm writing all this is more for recalling notation more than anything else. Now, one of the nice things about this correspondence between a matrix and a linear transformation is that, so proposition, again, I'm not going to prove this. Rudin has a proof, but you can work it out yourself. If I compose two linear transformation, if S belongs to Rn, Rm, and T is in Rm and Rk, let's say, so let me write let let's take this, if x1, x2, xn, y1, y2, ym, z1, z2, zm, zk are basis of Rn, Rm, and Rk respectively, then before I yeah, okay, let me introduce the notation here itself. See, when I introduce this the matrix of T, I called it as denoted it by this A, capital A. It's which was somewhat arbitrary. I mean, but the more standard notation is, which shows its dependence on T. One also writes it as T and then put square brackets around that. In fact, to be even more precise, if one calls this basis B1, capital B1, and this by B2, one can put a B1 and B2 right here as a subscript as well. But let me not do that, since anyway we'll just be working with standard basis most of the time. So let T belong to this, S belong to this, and okay, right, basis. Then the matrix of the linear transformation T composed with S. Now this matrix will have to involve the basis Z1, Z2, Zk and X1, X2, Xn. This will be just a matrix product of T with the matrix S, where of course this T is computed with respect to this Z1, Z2, Zk, Y1, Y2, Ym basis, and S is computed with X's and Y's. Then, so this is a very important and what makes the whole correspondence work very well. The fact that, in fact, matrix multiplication, on first sight, it seems it's not obvious how anyone came up with that notion of multiplication, but this explains why we define matrix multiplication the way we do. Namely, one just looks at the matrix of a composition, then it turns out one can get that if we define matrix multiplication this way. Right. Then there was one more thing. Yeah, okay, fine. That's it, I guess. Right. So let me just formally state this as a proposition. Let M, this is an M, capital M, NMR, be the set of N cross M matrices. Oh, no, not N. Here I got M cross N. M rows and columns, right. M cross N matrices. This is a vector space with the usual addition of matrices. We know how to add matrices of the same size. We just add the entries, corresponding entries. And we also know how to multiply a real number with a matrix. We just multiply every entry with that real number, and with the usual addition of matrices and scalar multiplication with a real number. So the claim is that, yeah, so these two operations, it becomes a vector space. And not only that, well, and we already know that the space of linear transformations is also a vector space. So there are two things. One is the dimension of this vector space, M n M R, is n times M. One can explicitly write down a basis, which is the analog of the standard basis. Just put in the ijth entry, you put 1, elsewhere you put 0. This is one thing. And then L Rn Rm is isomorphic to NMR as a vector space. Isomorphic, of course, here just means that there's a one-to-one onto linear transformation from Ln Rn Rm to MNR. So this map, given a linear transformation, associating a matrix to that is what we just discussed. I leave it to you to figure out, prove. It's a trivial thing to check, but it should be done anyway, that this map is bijective, associating a linear transformation to its matrix. So as a result, combining A and B, we see that the space of linear transformations is just a vector space of dimension R, is a vector space of dimension n times m, and therefore it's just R n m. The next thing is See, we had a norm on this space of linear transformations, namely the operator norm. Actually, we had a whole bunch of norms on this vector space. Every time we put a norm on Rn and a norm on Rm, we get a corresponding operator norm. So, but if we just stick to the standard Euclidean norms on these two Rn and Rm, we have a specific norm, operator norm on Lrn, Rm. But on the other hand, in space of matrices, there are other natural norms which sort of things one immediately thinks of. Namely, if I take a matrix, for example, I can regard it, as I said, you can put all the rows side by side or columns side by side and regard it as an element of Rn times m. So you would be in familiar Euclidean space of a large dimension. And there you have lots of norms like the Euclidean norm, LP norm, and so on. So this proposition relates the operator norm with that. So let T be a linear transformation. Then the operator norm of T is less than or equal to summation Tij squared, summation over all I and j, and then square root. Now, what is, of course, this Tij is just the entries of this matrix. So I equal to 1 to m, j equal to 1 to n. The entries of this matrix corresponding to T. So let's quickly prove this. So we start by looking at, let x be in Rn. Let's look at Tx, norm of the squared. Now we know that Tx, well, let's go back to this point here. The Tx has these coordinates here, which I wrote in the top of the page. And when I look at the Euclidean norm of Tx, I'll be just squaring all these terms and adding them up. So this is square of Aij, Cj, no, I used T, so let me stick with that. Tij, then square, so this is over j, which will be less than or equal to, now I use something which I have already done, the Cauchy-Schwarz inequality. J Aij squared, again it should be T, Tij squared, and then again Cj squared, which is now this Tij squared Well, see here, this is, here I'll have to sum over I and j. Now what I'm do is that observe that this Cj squared is just the norm of x squared, that's all, Euclidean norm of x squared. By the way, here actually I should be a bit careful here. For this proposition to work, I should specify something. So assume that I'm working with, the assumption is that this x1, x2, xn and y1, y2, yn be the standard basis. Standard basis. Actually, just any orthonormal basis will do, but let's just stick to standard basis. Then this is, everything works out fine. So, because one is working with the standard basis, then this Cj squared is just norm x squared, the standard Euclidean norm, right? And in fact, even the first line, norm Tx squared, is given by this expression here. This thing here works because we are working in standard basis. So, and this, what did we conclude? Well, we got this is less Tij squared summation over I and j. Now I divide so we assume x not equal to 0, and then therefore norm, or if I can just assume norm x less than or equal to 1, either way, then I take sup over all x and then take square root. So this will be less than or equal to summation Tij squared, summation over I and j. So in short, the operator norm, what we have, the operator norm is less than or equal to the standard Euclidean norm of a matrix. So therefore, in words, the operator norm is less than or equal to the Euclidean norm of the corresponding Euclidean norm of the corresponding matrix. So this will be, we'll soon use it. So this ends my brief discussion of matrices, and then next I'll talk a bit about metric spaces. Okay, let's stop here.